Welcome, Battletech enthusiasts. Today we're going to discuss the real-life physics of jump ships and what it would take to actually jump a jump ship 30 light years, like in Battletech, possibly by creating a wormhole and going through it using some sort of a jump drive technology, or possibly doing something more advanced called a brain jump, that is BRANE, which is related to string theory and high-energy particle physics. In case you've forgotten how to do matrix multiplication, I'm going to show you right here. And so ABCD times EFGH, and this is how you do it. You can consider this part here like a test. If you don't like this level of detail, it's time to stop watching now because this video is not for you. If you like it, then this video is good. Okay, this next step is called the trace of a matrix. Basically, all it is you sum up the diagonal elements. That's it. Now, it turns out those elements don't have to be numbers. If they were matrices inside, then you'd end up with a trace of a super matrix that had little matrices as the outputs. And here's how you would write down this as a matrix M with index components U and V. U can be 0 or 1, or V can be 0 or 1, depending on whether you're talking about A, B, C, or D. Those are kind of like the coordinates of the numbers in the matrix. So here, trace written out in this way would look like that. But before you do stop watching, in case you didn't like the detail there on the matrices, consider the following. If you just bear with me, you will suddenly, at one point in this video, understand exactly how a jump drive on a jump ship actually works and how it would go about creating a wormhole in the structure of space-time to make a jump. That's pretty cool. All you have to do is kind of bear and grin it through some math, which I will hopefully intersperse with pictures and things every once in a while. In the lab, physicists shoot lasers through slits and various patterns to create interferograms. Here you can see the famous two-slit experiment. Basically, half the light goes through one slit, the other half goes through the other slit, and it creates this interference pattern on the wall. Now, in a very bizarre fashion, even matter particles do this. So if you shoot a neutron or single electrons, even single electrons one at a time, shoot them through two holes or slits in a plate of metal, it creates an interference pattern too. The Michelson-Morley interferometer was designed to measure our speed through space. And this is like a famous experiment originally in the 1880s, but now people do this with lasers. But anyway, it measured a null result. This is like the most famous null result in history. The idea is that because the Earth is orbiting the Sun, the Earth must be moving in space. Therefore, we should be able to measure a difference in the speed of light in one direction versus another. I mean, after all, we are moving in space into a direction, and so light must be slower in the direction of motion. Except this is not what happens. No matter how you turn the interferometer, it always measures the speed of light as the same. And even more bizarrely, someone who's just a bystander on the side thinks light is moving along with them and not with you, even if you grab the interferometer and move at a high speed. This means, unlike sound, light doesn't have any medium that it travels through. It just magically and mystically always travels at the same speed according to anyone that sees it. So this means even if you're moving at 99% of the speed of light and you shoot light away from you with a flashlight, you think that light is moving away from you at 100% of the speed of light. And someone standing on the side sees you moving at 99% of the speed of light, and she sees the light from your flashlight moving only 1% as fast as the speed of light away from you, but exactly at the speed of light according to them. This topic is called special relativity, and it's usually combined with classical electromagnetism or classical physics for physics majors, because it's actually considered an elementary topic these days. Now, in order to explain all of this, you have to do something called use 4 vectors. 4 vectors are basically time as your 0th coordinate, and x, y, and z are your next 3 coordinates. And you have something called the boost matrix, and you do matrix multiplication of 4x4 matrix on your 1x4 vector of your space-time position to find out what your coordinates are if you were to be moving at some velocity. Now, within electromagnetism, there is a 4x4 matrix that's called the electromagnetic field strength tensor, and it describes how electric fields and magnetic fields are and how they interact and within even with relativistic physics. And that is because you can just multiply these 4x4 Lorentz boost matrices with this electromagnetic field matrix, and they all work together. Now, this is considered classical electromagnetism, and this electromagnetic field strength matrix is actually called the tensor. And even electrical engineers might be familiar with it, but not always, but physicists definitely are. Another feature of solving the Michelson-Morley interferometer problem is that you have to have a concept of a future and a past and a now. And the now is like a perpendicular to your time axis if you are not moving. So your future is kind of the z-axis, the past is the negative z-axis, and like your xy plane would be your now. That would be in a two-dimensional thing, whereas z was time, but really it's xyz three-dimensional, of course. Also, because there's also a concept of a light cone, and that is because in special relativity, forces can only travel at the speed of light. Therefore, nothing can touch you or affect you that is not inside your past light cone. Like if it's in the future, it doesn't count, and if it's in the now, but any distance away, it doesn't count because it can't touch you. So only things in your past light cone can affect you. Light thinks all time is zero. Needless to say, this is not how things work in Newtonian physics, but it is how things work in relativistic physics. And in fact, your here and now is tilted depending on your motion, and it gets distorted. But there is a strange thing that everyone agrees on, and that's called the interval. And that's if you measure distance, instead of measuring it in a Euclidean way like here with the Pythagorean theorem in 3 dimensions, you instead add a -1 factor on your time axis. You create something called the Lorenzian metric. And a metric is basically how you measure distance. Now, a tensor that has 2 Greek indices, like 1 up and 1 down, or 2 ups or 2 downs, is basically just a matrix. If it has 3 indices, it's basically a cube of numbers. And if it's just 1 index, then it's more like just a vector, because it has a single, like a row of numbers. Now, this spreads arbitrarily to an arbitrary number of dimensions. So if you have 4 indices, then you have a hypercube of numbers. Pairs of indices have special statuses because you can take traces, or i.e. do contractions on those axes. Because it's hard to visualize 4-dimensional hypercubes of numbers and whatnot, sometimes it's easier to write down a higher dimensional tensor as rather an array of matrices or an array of column vectors or row vectors or something like that. So here I'm writing this 3-component tensor as a array of vectors. This is like the very intro to tensor calculus. So you see here that I've created this, or showing you this equation. This NUV is the metric, and that is it's the identity matrix 1 1 1, a 3x3 matrix that's all ones in the diagonal if you are just living in Euclidean 3-dimensional space, and it's -1 1 1 1 on the diagonal and all zeros elsewhere if you're living in Lorentzian or special relativistic space. Now I'm going to show you the dot product of a vector with itself using this kind of notation. Now the vector is t, x, y, and z. When the index is down, I'm going to treat it as a row vector, and when the index is up, I'm going to treat it as a column vector. Or you can see here basically a matrix of 1x4 versus 4x1. When you multiply them together, you just multiply the components together and add them together after multiplying the components with themselves. So t squared plus x squared plus y squared plus z squared. Now, when you add this metric to it, it acts a little differently, even though I'm kind of glossing over some steps here about how the indices rise and lower and how they commute with the matrix. But I'm just going to show you. Row vector, matrix, column vector becomes this structure. Now here v and w are just regular vectors, and you can see here the dot product is being shown here. Tensors are written in that way where that metric is in the front and the two vectors have that u and that v on them. Those just represent the x, y, and z axes. So u equals 0, 1, or 2, depending if you're talking about x, y, or z, or actually it's 0, 1, 2, or 3 if it's time x, y, or z. Now bear in mind that this is all just normal, boring special relativity still. And now we're going to also, it turns out that whether the sign of the interval is positive, negative, or 0 determines whether two events or objects are considered separated by time, by space, or light. And now I'm going to work out an explicit example. Okay, so now what I'm going to do is here's drawing the space-time coordinates. I'm going to put 2 points down, here and here. And you can see the separation in the x-axis is 4. So I'm going to say delta x is 4. And the separation in the time axis is 1. And the delta y and delta z, I'm just going to say are the same, so it's 0. Now, to figure out what is the interval here, I'm now going to use the Lorenzian metric. Remember, this is all just normal special relativity still. And I'm going to multiply this out. And here I'm going to multiply out this matrix by, I'm going to first multiply the matrix in the middle by the column vector in the back. And then what I'm going to do is I'm going to then take these two, the row vector and the column vector, and then just multiply them with each other. You can see here, I'm getting -1 plus 16. So the total is 15. So it's a positive number. It turns out, remember, if the distance or interval is greater than 0, it is a space-like separation. Now I'm going to take these two objects and separate them here. So delta time is 2, delta x is 2, delta y and delta z are 0. And now I'm going to write out the space-time coordinates and the Lorenzian metric, space-time coordinate difference. And now I'm going to do the same thing again. And this time, as you can see, you're going to get -4 plus 4 plus 0 plus 0. That's 0. So that is a light-like separation, i.e., that is the separation between 2 points that are separated by a photon, which means 0 time elapses as photons see 0 time. And then now I'm finally going to do the final one here with a time-like separation, because the delta x is 1 and the delta t is 3. And you can see here, except I've kind of gone off camera a little bit, so I'll have to scroll the paper over. But I got -8 as the interval. And remember, if it's negative, that means you have a time-like separation. That means it's possible from you, that means that it's possible if you're in the bottom point, that top point is in your future. You can get to it because it is a time-like separated point from you. So anyway, that's all special relativity. Now here there's a generic definitions of tensors and how they interact with each other, and you can see these up indices and down indices cross-annihilate each other. Oh, and by the way, the Lagrangian of space-time as written in the Lagrangian format that we discussed in the Lagrangian orbit video looks somewhat like this. There's also a couple other odd symbols that look like tensors but actually are not tensors. This is called the Levi-Civita symbol, and it's just a tool for manipulating signs and indices to move them up and down. Now, still within special relativity, you can look at particles as exchanging photons like this, or even photons as exchanging particles like that. That's something related to quantum mechanics and field theory, but that's still within the realm of special relativity. Special relativity is actually the statement that you're living in a Euclidean manifold, that is, space-time is flat and there's no curvature. But now we're going to start discussing general relativity, and this is where things get cool. This will hopefully save you a few years of study. I used a bunch of books when I studied, and these are some of them. Someone I knew wrote this particular one. He's a really smart guy. He's now doing this for a living. But before we get to the cool stuff, we have to go back to Newtonian gravity and boring special relativity and whatnot. First, these are the equations of Newtonian gravity. Basically, F equals ma and F equals gmm over r squared. These describe Newtonian gravity. This is another set of equations that also describes Newtonian gravity, even though it looks very different. That's because you can actually have many different sets of equations that look very different that are actually describing the same idea. And now this is again the electromagnetic field tensor. This is basically what the coil in a jump ship would generate in its attempt to distort space-time in order to create a wormhole. Now this is something called the stress energy tensor for electromagnetism. It describes how much energy there is stored in the electromagnetic field. Now this one here is the complex version that includes the local space-time metric. And now this is the description of the stress energy tensor form of the distribution of mass. That symbol on the left means how mass is, that's like the density of mass. And the fact that mass energy fluid is conserved means that you can create something called a Gauss's law in space-time of the conservation of matter energy fluid. Now, if you have a perfect fluid of mass energy, you get this kind of a formula. This is the stress energy tensor of mass energy fluid. Now I'm just going to give you the answer. This is the equation that describes how the curvature of space-time on the left interacts with the matter energy fluid distribution, which is on the right. Now you're not expected to understand this formula right now, but here's the answer. And the final key component to building a jump ship is the Riemann Curvature Tensor. This describes how space-time is curved. Okay, so this is a 4-index tensor, which means it's actually a hypercube of numbers. But since that's very hard to kind of visualize, people will often think of this instead as a matrix of matrices. So each element of this matrix is actually a matrix of its own, and this makes it a little more wieldy. Now, each of these matrices has numbers in it, but remember, these numbers can actually be functions too, and that's generally how it is. These are functions of the mass distribution of space-time. Where does this Riemann curvature tensor come from? Now, I said before that it's a measure of curvature, and how it works is if you move a vector around by parallel translation, and you move it around in a closed surface, and if it comes back to the original location unchanged, then you are on a flat space. Like a sheet of paper is a flat space. If you parallel transport a vector, it comes back. If you do it on a ball, though, you get a totally different result. Here I'm parallel transporting around the equator. Now I'm going up to the North Pole, and now I'm going to come back down to the equator, but the vector is pointing in a different direction than when I started. That's because this has curvature. Now, if you fold a sheet of paper, but you don't fold it, you just kind of curve it like this, it still does not have curvature because you can parallel transport a vector around. But if you draw a triangle on a ball, you also notice its angles don't add up to 180 degrees. So these are two key features of curvature. So the ball has a missing angle when you draw a triangle, and the sheet of paper, even though you curved it in one axis, is still considered flat because parallel transport does not cause rotation. Now let's look at the definition of the Riemann curvature tensor. It has these upside down triangles on the right side, which represent slopes or derivatives. And if you put it on a flat sheet, you end up getting 0 because you subtract the slope in one direction and slope in another direction times a vector, and then the other slope and the other slope, you end up with 0. And if you put it on a curved surface, you'll end up with a non-zero value. There's a concept called a contraction, which is, if you notice how R, A, B, C, B up, there's a B is up and a B is down. That's called a contraction on a B. That's equivalent to summing over that index. Like, that is, you take B equals 0, B equals 1, B equals 2, and B equals 3, and you find the values and you add them up. And here's how you actually do contractions. So here's our A, B, C, B. So first, you remember that this was a hypercube of numbers, or a matrix of matrices, to try to keep track of it better. And I'm going to have these two directions or dimensions in the array of arrays represent the B and D axes. So that's what you're contracting on. Since we're contracting on that, it means we're going to take the matrices that are in the diagonal of this matrix of matrices and add them together as the result. And that's how you do the contraction. It's kind of like a trace, except we're doing it on matrices. And here's yet another sum. This is basically taking the matrix RAA, and it turns into a scalar when you sum R11, R22, R33, and R44, and that 4x4 matrix becomes a 1x1 number. And here I'm going to just explicitly do it, except without components. I'm just keeping generic components inside because it's going to be otherwise spend a huge amount of time. So there's, for example, let's pretend these are the matrices that we got out from the original contraction. And now, so I'm looking at those, and basically the components of the matrix that results gets traced into a single number. Einstein realized that this particular combination of Riemann contractions has value, and therefore this tensor is called the Einstein tensor. Using something called advanced diffeomorphisms, you can prove that this GAB has this strange property with this upside down triangle in front of it. Here we are rewriting some of the symbols in more familiar terms using partial differential notation, and then we're plugging and chugging in some of these values in. Skipping many steps that if you want to see, you can go look inside these GR books. You end up with this Einstein field equation. This is the final full equation that describes how mass energy and stress energy tensors and the structure of space-time interact. You can also derive something called the geodesic equation. This equation describes how a weightless or free-falling object travels inside the structure of space-time. This is known as a geodesic. Now, if you just find solutions to the Einstein field equations, you can find that if you have a mass, m, like a planet, it creates a curvature in space-time somewhat similar to this diagram here. Now, if you take a gravity well and cut it in half where the mass is, and attach another matching gravity well to the other side, what you find is you actually don't even need a mass anymore. This tube structure is called a wormhole. So how would a jump ship use its KF drive to actually create a wormhole? Well, first it would have to fold space. Then it would have to use the electromagnetic field tensor by using some massive electrical burst. And then it would have to distort the structure of space-time to create the wormhole. There is, however, one subtle detail. This electromagnetic field tensor is anti-symmetric. If you look across the diagonal, the signs are the opposite. Like E1 is the opposite to minus E1 if you look across those diagonals of zeros. That's called an anti-symmetry. An anti-symmetric matrix does not talk to a symmetric matrix easily, and mass energy fluid in space-time structure tends to like symmetric structures. Needless to say, this is a significant technical hurdle to overcome. Now, how would a jump actually occur? First, the jump ship would fold space. You can see here it's going to bring some drop ships along with it. Then it would open the wormhole. Here it's actually opened the wormhole. Then it would plunge in as if it were just crashing into a planet, except it would shoot out the other side, come to rest. Then it would close the wormhole. Then it would go ahead and release the drop ships. And oh yes, payback is coming, you damn KURITANS. Payback. Scout report is complete. There was nothing to see here. This whole area is on fire. There are no KURITANS present here anymore. Now, how can we trust general relativity? Well, for one thing, it has to be able to reconstruct Newtonian gravity. And this is a concept called universality. Any more advanced theory has to reconstruct the previous, more primitive theory in the low energy limit. Otherwise, it's a junk theory. So next time somebody comes up to you and says, oh, I've got this grand theory of everything, and in some kind of strange crackpotty fashion, ask them to prove that it reduces to the existing standard model. If it can't do that, it's not a valid theory. Now, your eyes may glaze over a little bit here on some of the math, but I'm basically making a perturbation on a flat metric, and I'm doing something called Christoffel symbols, which describe curvatures in space-times, and then how these Christoffel symbols interact with the Ricci tensor, which is that contraction of the Riemann tensor, and the Einstein tensor goes like this. This is how it transforms using differential operators, some more fancy math, and finally, this turns into the linear Einstein equation, and we do more fancy math, pop in for the geodesic equation, figure out Christoffel symbols, and out comes Newtonian gravity. If you want more real life physics content like this, then please subscribe, and I will be glad to make more videos and you will know about them. Thank you.